Hello, everybody. Good afternoon. Okay, so yesterday I talked about representation ability of a neural network. And so first I talked about the universal approximability of a neural network. So that means the neural network can approximate any function with any precision. And next, I talked about the adaptivity of deep learning. So deep learning has some adaptivity, and because of that, it can outperform the kernel method. So this is closely related to feature extraction ability. Okay, and so today I would like to first talk about the generalization ability of a neural network, and then I will go to the optimization ability. So the topic of optimization ability is the main part of today's tutorial. But before I will going into the main part. So I will talk about the generalization ability of a neural network. Okay, so but I will skip this section. So double descent and binary overfitting. So double descent and binary overfitting is one of our very hottest topic of today's deep learning theories. But I guess if you have attended Peter Bartlett's tutorial, I guess he have already mentioned something about this. So therefore, I will skip. Oh.
Yeah, Taiji, unfortunately, he ran out of time and did not cover
really?
binary overfitting.
Oh, I see. Okay,
but anyway, go ahead with your plans.
Okay, I see. Thank you. Okay, but well, I will be also short if I will talk this topic. So I will skip this one, and I will directly go into the generation gap analysis. Okay. Okay, and then after that, so I will talk about optimization ability. Okay, so let's start. Okay, so when we talk about the generalization ability of a neural network, so we should always take care of the overfittings. Okay, so if the model has a less parameterized, I mean, so if the model is not so expressive, so the model is very simple. So then that model cannot be fit to the data. So then there happens the underfitting like this. So the model cannot explain the training data. So the training error is large. So this is called the underfittings. So so it is a little bit easy. It is rather easy to detect the underfittings. So because the training error is large, so it is rather easy to detect that. So therefore, by increasing the model complexity, so we would think a better fit like this. Okay, so this is a very nice fit. So although the training error is not zero, so its predictive error is pretty good. That if you increase the model size furthermore, so that you get this kind of fit. Okay, so the training error is almost zero. So in that sense, this fit is very nice. Okay? So in terms of training error, so this fit is very nice. But you see that there are large deviations. So the test error should be very large. For example, if the new data point will come here, so you suffer from this kind of large errors. So this is called overfittings. So if you read the machine learning text, so it is always taught that so you should avoid the overfitting. Okay. Yeah. So therefore, we need to select the appropriate size of the network to obtain appropriate fit like this. Okay. So the same thing can be applied to the neural networks. Of course, if you use very complicated neural networks, you suffer from the overfitting. So therefore, it is natural to think that you should avoid the overfitting by reducing the model size. But in practice, we usually see that the neural network can avoid the overfitting, even though its model complexity is very large. Okay, so the horizontal axis is the number of parameters. The vertical axis is the test error and the training errors. Okay, so now you increase the number of parameters. Then, so at some point, the test error gets zero. So here we are considering the classification task. So the training error can be zero. So we are not looking at the loss function, but we are looking at the classification error. So then it can get zero. Okay, so this point, at this point, it is like overfitted. Okay, so but So furthermore, so even if you increase the number of parameters, so then the test error still drops. Okay, based on the classic learning theory, so maybe so it is expected that the test error will going up because of the overfitting. But in practice, we sometimes and usually observe that the test error still drops like this. The test error continue to drop. Okay, so why is it? For example, if we consider the ImageNet dataset, the data size is like 1.2 million. And also the model parameter size is like 1 billion. So if you use ResNet or some more larger network size, network model, so then it can likely be greater than the 1 billion. So therefore, the number of parameters in the model can be easily larger than the data size. So this is called overparameterization. So the question is, so why the neural network can avoid overfitting, even in this kind of overparameterized settings? So this is one of the biggest issues in deep learning theories. Okay, so now, so we turn back to the classic learning theories. Suppose that model F has a d-dimensional parameters. Okay, so then the predictive error is roughly bounded by like this. So the model dimensionality d divided by sample size is the variance, and it's plus the bias term. Okay, so if you consider very large network, maybe so this approximation error, the bias term could be very small, but the problem is the variance. Okay, so if you use overparameterized network, so d is larger than the sample size, so this variance is greater than 1. So therefore, this kind of naive evaluation does not explain why such an overparameterized network can generalize. Okay, so therefore we need some other approaches than this kind of a very classic naive evaluation. Okay, so one approach is the double descent and benign overfitting. So, but okay, so I would like to skip this one. Okay, so but I would like to go into the generalization gap analysis. Okay, so okay. Okay, so now, so we are interested in the number of parameters. We are interested in the settings of the overparameter settings. Okay, so to analyze the generalization ability of the neural network. So a common approach. So one of the typical approach to analyze the generalization gap like this. So we bound the gap between the expected error and the training error. Okay, so if these two quantities are very large, so then it causes overfitting. But if these two quantities, the expected error and the training error, are very close, so then it doesn't cause overfittings. So therefore, looking at the generalization gap is very important. And so yeah, analyzing the generalization gap is one of our very typical topics of machine learning researches. Okay. For example, if you look at the theoretical papers appearing in the conference, like NeurIPS and ICM, there are many bounds. So that bound the generation gap. Okay. So now, so we want to bound the generation gap for the neural networks. So especially for the overparameterized network. Okay. And so now, so we apply a very naive bound, so-called BC dimensional bound. Okay, so you apply. So BC dimensional bound is very maybe so the first step bound to obtain the generation gap. Okay, so if you apply the BC dimensional bound, so you get this kind of bound. It is a square root of the number of parameters divided by sample size n. So where ML is the width of the Lth layer, and ML plus 1 is the width of the L plus 1 layer. Okay, so basically this is the number of parameters. So because the internal layers there is a weight matrix, the number of parameters in the weight matrix is ML times ML plus 1. By taking the sum of them, so we obtain the number of parameters. Okay, so yeah, we have a clear upper bound of the generation gap. But the problem is that, so here is the number of parameters. So this bound cannot be applied to overparametered settings. If the model is overparameterized, the number of parameters is much larger than the sample size. So we cannot use this bound to express the generation ability of neural networks. So therefore, we need some other bound. Okay, so the common approach to obtain the better bound is that it's to measure intrinsic dimensionality. So instead of counting the number of parameters itself, so we count the intrinsic dimensionality. So in other words, effective dimensionality. So maybe the number of parameters could be very, very large, but its essential dimensionality could be pretty small. So we measure that. So yeah, okay, so I have one question. Why in machine learning some years back, cross-validation approaches used to assume test error goes up at some point, at which point the training must stop, whereas overparameterization and generalization discovered by accident. Okay, the cross-validation approaches used to assume test error goes up at some point, at which point the training must stop. Okay, yeah, so of course that okay, so okay, please let's go back to this figure. Okay, so this is the classic bias and variance trade-off. Okay, so this is usually observed. So if you run the very simple machine learning models, so then we usually observe this kind of curve. So yeah, so this kind of bias and variance trade-off is very common in many machine learning models. For example, so if you're using the linear models, so then without any regularization, so you observe this curve. Okay. So therefore, we needed to stop. We need to cut the model size like this. So we need to choose the best model size around here. So this is true. But these days, so there are many occasions in which we deal with very high dimensional models. Okay, for example, neural network is one of them, and also the kernel method is also a very high dimensional model. So anyway, so but if we use such a very high dimensional model, so then we observe this double descent. Okay, so this is a kind of a well, accident. So this is a kind of accident, but this is not so new. So this kind of phenomenon was already discovered in 20 or 30 years ago. Yeah. So therefore, this is not so much new. So by running many experiments, so then the people have already encountered this kind of a phenomena. So yeah. So it is not so accidental thing. Okay. And also I should say that the kernel method is already infinite dimensional model. So with appropriate approximation, with appropriate regularization, so you can avoid overfitting. So yeah. So one approach is choosing a good size of the model. The another approach is the regularization. So okay. So thank you very much. So now I'm going to next slide. Okay. Okay. So the one important approach is to find the intrinsic dimensionality. Okay. And actually, in reality, so to run the deep learning, so we use many regularization. For example, we use weight decay and drop out and batch normalization. So we are using many explicit regularization. And there are also implicit regularization. For example, if you run the SGD, it traps at some local optimum, but that local optimum could be nice for the generalization. So it is like an algorithm inducing bias. So there are many bias. So interesting. There are many interesting bias. So yeah. So anyway, so through such a regularization, so the intrinsic dimensionality of a neural network can be small. So this is one example. So if you look at the features in the internal radius, and you compute the covariance matrix of the features, and then we calculate the eigenvalue of the covariance matrix of the features in the internal radius, then it looks like this. Okay, there are few number of large eigenvalues, and there are many numbers of small eigenvalues. Okay. So then the informative part is only around here. So these small eigenvalue parts are almost noise. So around here, so there are no information. So we can neglect this point. And the informative part is only here. So therefore, the intrinsic dimensionality could be very small compared with the whole dimensionality. Okay. So we want to count or measure this kind of intrinsic dimensionality. Okay. This is also very important to analyze benign overfitting. But anyway, so we consider this kind of thing. To measure or to quantify that intrinsic dimensionality, there are some approaches. One is a normal-based bound. Okay, the second is the degrees of freedom analysis. So in other words, the compression-based bound. So I will introduce both of them. Okay, so here is some summary of the bounds. Here is the normal-based bound, and here is the naive DC dimension bound, and here is the compression-based bound. So I will explain briefly these bounds. Okay. So maybe you know that to obtain the generation gap, so it is important to consider the uniform bound. Okay. So this is what we want to bound. And we want to bound the difference between expected loss and the training loss. Okay. But the problem is that the estimator F hat is dependent to the training data. So this is not an IID sum. So this is not an IID average of random variables. So therefore, we cannot apply the naive central limit theorem or the law of large numbers or Hoeffding inequalities. So therefore, instead, we should consider this kind of a uniform bound. Okay, so because we don't know where F hat is, so we take the Spree-Mann in the model. So this is called the uniform bound. To bound this uniform bound, so we use the Rademacher complexity. Okay, so Rademacher complexity is useful to bound this uniform bound. And also the Rademacher complexity is bounded by so-called Dudley's integral or something like that. So this is a kind of recipe to obtain a generation gap. Okay, so these bounds, so the bounds shown in this table, so all of them tries to bound this Rademacher complexity of the set of the neural networks. But the problem is that, so if you consider the whole set of networks, so then there appears a BC dimensional bound. So BC dimensional bound is actually tight. So if you consider the set of the all networks, so then the Rademacher complexity, it can be bounded by only the BC dimension bound. So BC dimension bound is also the lower bound of the Rademacher complexity of the whole set of the networks. So the BC dimension bound is a kind of tight bound. So okay, so therefore, to obtain a better bound, so we should consider some subset of the all networks. Okay. So to do so, we consider a set of the typical networks that can be obtained by training. Okay, so the networks that is typically obtained by the training is a little bit small, very basic. That set is very small, so compared with the whole set of the networks. So then maybe so we can obtain a tighter bound. Okay, so to characterize this small set of networks, maybe we can consider the bound of the norm. Okay, we assume that the training network has a kind of bounded norms. Okay, so we consider we look at the weight matrix in each layer, and then usually the training network has a bounded norm of such a weight matrix. Okay. So then such a norm constraint restricts the set of the networks. So then maybe we get a better bound. So using such intuitions, the many norm-based bounds have been proposed. The one of that is given by like this. So this is a very famous bound. So this is called the spectrally normalized margin bound. And so, well, the important point is that this bound is obtained by only the weight. The norm of the weight matrix. Okay, so RL2 is the operator norm of operator norm of the Lth layers weight matrix. So that means that the maximum singular value of the weight matrix. And RL21 is so-called 2-1 norm. So that is given by the sum of the norm of the jth row of the weight matrix. And so anyway, so there doesn't appear any model size. So for example, width or something like that doesn't appear in the bound. So therefore, so this kind of a bound can be applied to over-parameterized models. Okay. So actually, this normal-based bound can be applied for the infinite width network. Okay. So even though the width is very, very large, so if the norm is bounded, so then this gives a tight bound. So that's good. So there are also some variants of this kind of bound. So the one is the Pack-based bound. Okay, so instead of RL21 norm, so there appears a so-called Frobenius norm. The Frobenius norm is given by like this. So this is a kind of L2 norm of the weight matrix. And there is also another bound given by the Gorovich et al. Okay, so instead of the maximum singular values, there appears a Frobenius norm. Sometimes the Frobenius norm is smaller than the R21 norm. So yeah, using the Frobenius norm is beneficial. So anyway, so there doesn't appear the model size. Yeah, here is the model size, the width for the network, but there doesn't appear the quadratic order dependency of the width. So this is much better than the BCT measure bound. Okay. So, but the one drawback of this kind of bound is that there appears, there appears some power, exponential order dependency to the norm. Okay, so let's go back to this bound. You see that there is a product of the maximum singular value of the weight matrix like this. So if we consider a very deep network, this is an exponential order to the depth, exponential to L comes here because here is the product. So that could be very large. So actually, from some experimental numerical experiments, so it has been reported that the log over the bound can be very large. So actually, even though if you increase the training set size, the log of the bound increases. So, but the generation gap should decrease as the models the generation gap should decrease as the training set size increases. But so that bound, so this kind of norm-based bound increases as the training set increases. So this is not good. So this is mainly because of the product of the norm of the weight matrix. So because of this product, because this is an exponential dependency, and so therefore, if the weight matrix is a little bit large in each layer, so this exponential order term could be very large. Okay, so this is one drawback of this kind of a bound. But there's a way to overcome this problem. So that is to replace this quantity by another smaller quantity. Okay, so this quantity, so this product of the weight matrix is coming from the Lipschitz continuity of the network. Okay, so you input some input X, so then we get an output Y. So then if you part up X a little bit, so then Y will also part up. So how large the Y should part up for a small perturbation of the input X. So that magnitude is measured by this Lipschitz continuity. Okay, so in each layer, the Lipschitz continuity is measured by the operator norm of the weight matrix. So by taking its product, we can naively bound the Lipschitz continuity of the neural networks. Okay, so I have a question. What kinds of training sets are used to evaluate these bounds? Is it significant? Which training set is? That's a good question. So, as far as I understand, so this is a very simple classification task. So, okay, so yeah, of course, it must be dependent on the data sets data set, but usually we have a very large bound for usually we observe a very large value of this product. So, for example, if we use a classification task like a cipher 10, so very common data sets, this is a very common phenomenon. Of course, cipher 10 or MNIST and also the ImageNet data set. So you actually observe this kind of a very large quantity of the bound. So I don't think this is not so much specific to that data set. Yeah. Okay, thank you. Okay, so but anyway, so this bound is very loose because this is a very loose bound to evaluate the Lipschitz continuity. So therefore, we can replace the Lipschitz continuity for a data-dependent one instead of using this kind of a very large upper bound. So we can use some data-dependent Lipschitz continuity. Yeah. So so then we can obtain a beta bound. So yeah, so then we have a much better one. So this is called the Lipschitz augmentation technique. Okay. Okay. Oh, okay. So I also have another bound, another questions. Do I understand correctly that is this setting we only consider architectures with only fluidly connected layers and do convolution? Yeah. You can also consider convolution layers. So just for simplicity of my explanation, so you can consider the convolution layers. Yeah. I just wonder how one can compute SPD or convolution filters. Singular value decomposition. I see. Okay. Okay. So anyway, the convolution filter is also a linear operator, so that you can compute the operator norm. So yeah, so that is how to compute the singular value or the operator norm of the weight matrix. So for the some input X, so some input image, so then you can obtain the output by applying the convolution. So then you can bound the norm over the upper norm over the output. So the maximum value of the maximum value of the norm of that output is the operator norm of the convolutional filters. Yeah. And so for more details, so please look at the papers. Yeah. Okay. So this is a norm-based one. So this is also good. And so there is another approach that is called compression-based one. So instead of we consider the norm, we count the so-called effective dimensionality. So here's one observation from this paper. Okay. And so this figure shows a kind of noise propagation. Okay. So here xi is the output to the ith layer, and x hat I is the output to the ith layer with some noise injection to the input. So we consider same input, but for the x hat I, we add some noise to the input. So then the output xi could be a little bit different. So we measure that difference. So how the noise is propagated through the layer is measured by this quantity. Okay, so we take the difference x hat I minus xi, and we divide by xi, the norm of xi. So this is the measure. So this is a kind of a noise propagation quantity. Okay, so we plot this with respect to the layer I. Okay, so then we obtain this kind of the graph. Okay. Okay, so there are many lines. So each line depends on the layer. So each line represents the noise propagation for the input. So it's, okay, so for example, if we consider this line, so then the input is the noise is injected for the 10th layers input. Okay, we input the input. We input x to the 10th layer, and we also inject a noise to that input, and then we see how it propagates to the later layers. Okay. Yeah, so this is the noise propagation graph. So and we see that noise propagation is decreased. I mean that the effect of the noise will be suppressed. So this means that each layer works as noise filtering. Okay, so each layer discard noise, and each layer only pass the informative features to the next layer, and it filters out the noise. So this can be done because the weight matrix is nearly low rank. Okay, so the weight matrix is nearly low rank. So if the weight matrix is identity, everything is passed. So then it cannot filter out the noise. So, but if the weight matrix is nearly low rank, so then random noise can be filtered out by the small singular values. So therefore, yeah, and so this means that the weight matrix in the internal layers are likely to be nearly low rank. So this means that the weight matrix can be compressed. That can be altered by the nearly low rank matrix. Okay. So this means that the network can be compressed. Okay, so here is an intuition behind the compression-based one. So suppose that we have very large network. So now we approximate this large network by a small network with a very small number of parameters. So then the effective number of parameters of the original network should be small. Okay, so instead of a number of parameters, we count the number of parameters of this compressed network. So then maybe it is a good measure of the interesting dimensionality. Okay, so then the question is when we can compress a network. Okay. But in practice, we see this kind of phenomena. So that means that so it can be expected that the trained network can be compressed as smaller network. Okay, so this is a typical compression-based one. Okay, so in the left-hand side, there is an expectation error of the compressed network. And in the right-hand side, there is a training error of the original network. And so plus, there is some bias term and plus some variance term. Okay, so the bias term is given by the distance between the original network and the compressed network. Okay, so the distance is measured by the empirical L2 norm. The L2 norm measured by the empirical distribution. And so the third term is the variance. The variance is basically the square root of the number of parameters of the compressed network divided by the sample size. So if the compressed network is very small, so then this variance term becomes very small. So you see that there is a bias and a variance trade-off. Okay, so if you consider a very small compressed network, so then the bias could be large. But if you consider a large compressed network, so then the variance term could be large. So there are some bias and the variance trade-off. But the problem of this kind of bound is that in the left-hand side, so there is a compressed network. So here is not an original network. Instead, so this kind of bound evaluates the expected loss of the compressed network instead of the original network. So the question is, what happens for the original network? Okay, so if you look at these papers, so all of these papers evaluate expected loss of the compressed network. Okay, I have one question. The number of layers need to be consistent during the compression. Okay, so that's a good point. You don't need to be consistent. So the number of layers can be changed. Okay, so we are concerned with compressing only number of weights. Okay, yeah, you can change the number of layers. For example, let us consider one layer. So then there is one weight matrix. So we compress that we approximate that weight matrix by a low rank matrix. So then in that case, that weight matrix can be decomposed into how to say, the wide network times, wide matrix times thin matrix. So then in that case, the one weight matrix is decomposed into two matrices. So then that situation corresponds to the two-layer networks instead of one layer. So it is decomposed into two layers. So then the number of layers is increased, but it is okay. Yeah. Okay, thank you. Okay, so this is a more a concrete expression of the compression-based bound given by Aurora et al. And our teams, but I skipped the details. Okay, so now, we turn to the expected error of the original network instead of the compressed network. And we can evaluate that. Okay, so remember that in the previous slide, so in the left-hand side, there was a compressed network, but we can replace it by original network like this. And by doing so, we can improve the bias term. Like R hat can be improved like 1/√n times R hat. So this is a significant improvement. So roughly speaking, this is because in the previous bound, so the R hat measures the difference of the training error of F hat and F sharp. But if you consider a consistent quantities in the left-hand side and right-hand side, so instead of measuring this one, so we just needed to measure this quantity. Okay, so the difference, the generation gap of F hat minus the generation gap of F sharp. So this is just a difference of a difference. So this can be much smaller than this quantity. So because of this, so we have a tighter bound. To measure this quantity, so we use the so-called local Rademacher complexity technique. But anyway, by using such a technique, so we can obtain this kind of improved bound. So because the bias is improved, so you can decrease the variance term. Okay, so yeah, you can reduce the quantity, the magnitude of variance term. So then you can get a good bias and variance trade-off. Then you obtain the tighter bound than the previous one. Okay, so then the question is, so we can compress, and how small the network can be compressed to. Here is one viewpoint. So when we can compress. Okay, so now we look at the weight matrix. So then we calculate its singular values. So then we usually see that the singular value decays very rapidly. Okay, and so we also look at the variance and covariance matrix of the features in the internal layers. So then we calculate its eigenvalues. So we again observe rapid decay of the eigenvalues. So this means that the weight matrix can be approximated by a low rank matrix. And also we can see that there are very many redundant features in the internal layers because the variance and covariance matrix is almost a low rank. So that means that all features are correlated each other very much. That means that the internal layers is a little bit redundant. So there are many redundant information. So you can discard those redundant information. So that means that we can compress the network to a smaller network. Okay, so now so how to count the intrinsic dimensionality? So to count the intrinsic dimensionality, so there is some threshold. So there is this threshold is a theoretically oriented threshold. So that is like a R hat coming here. So R hat is obtained by balancing the bias and variance trade-off, and so then the R hat is this threshold, and we count the number of eigenvalues larger than this threshold. So this is the intrinsic dimensionality of that layer. Okay, so in this case, the width of the network is like a 256, and so but the number of eigenvalues which is greater than this threshold is like a 20 over 13. So yeah, the intrinsic dimensionality is much smaller than the original network size. So here is a comparison of the network size with the original, comparison of the original network size and the intrinsic dimensionality. You see that the intrinsic dimensionality is much smaller than the original network size. Okay, so then we can virtually compress the network to this kind of smaller network. Why VGG layer 6 highest compression size? Yeah, so it is a little bit interesting thing. Yeah, so we typically observed that some internal layers shows the highest compressed size, and for much deeper layers we see very good compression. So I don't know why, but the intuition like that. So in the past and in the early layers, the shallow layers, we extract very simple informations. But at layer 6 or something like that, so there are many rich informations. In the past layers, we extract only very simple information, but by combining them in the internal layers, there appears very complicated and dense information. So maybe I guess it is very hard to compress because this kind of internal layers is very important. So we cannot discard that. Yeah. So after that, we have already extracted good information, so we can compress the network. So maybe we don't need that network. The layer size could be so large, but anyway. So yeah, so we usually observe this kind of phenomena. Yeah. Okay. So based on this kind of observations, we can obtain this kind of a bound. So if the singular value of the weight matrix decays like J2 minus alpha, and the eigenvalue of the covariance matrix decays like J2 minus beta. So if we assume this kind of a polynomial order decays, so then we can obtain this kind of upper bound of a generation gap. This is a kind of artifact of the proof. So this you can neglect this term. So the main term is coming here. So you see that there is a summation of the width. So yeah, because this is just a linear order of the width. So this is much tighter than the BC dimension bound. In the BC dimension bound, so we have a quadratic dependency on the width, but this is just a linear dependence. And also there appears some power. If beta and alpha is large, so this power is smaller than 1. So therefore, this could be like a square root of the summation of ML. So this is even smaller than the linear orders. So this is even smaller than the linear order dependency. So this is much smaller. Okay, so this kind of bound can explain the generation ability of overparameterized network. Okay. Okay, I skip this one. Okay, so then I would like to go into the optimization ability. Okay, so before I'm going to the optimization ability, I want to briefly mention about some practical implication of that compression-based bound. So there's a so-called big NAS technique. Big NAS technique is one of the NAS technique. So in that method, so we try to train very huge network. Okay, we train the huge network, so that huge network can be compressed after the training. But by doing so, we deploy the model to the edge devices. So we can select a small subset of the network, so that network can be fit to the edge device. So then it's useful. So during the training, the big NAS changes the width and the depth randomly. So by changing the width and depth randomly, so then the smaller subset of the network can simultaneously minimize the training data, the training error. So therefore, just after training, so it becomes easier to compress the network. Even though we extract the subnetwork, that subnetwork performs very nice, and it gives a good predictive performance. Okay, so therefore, the trained network can be easily compressed without fine-tuning. And an interesting observation is that so such a network has a better generalization performance than the vanilla training. Okay, so you see a better performance than the vanilla, vanilla trainings. So this means that the compressibility gives some regularization for the training. Okay? If the network can be compressed, it can be well generalized. So during the optimization, if you impose that trained network can be compressed, so then it works as a regularization. Yeah. So maybe that can be applied to the dropout. Okay, so the dropout works something like that. So the network can be compressed. Okay, so let's move on to optimization ability. Okay, this is the main part of today's talk. Okay, do you have any questions? Okay. Okay, did we discuss compression in order to deal with big size with overparameterized model? Did we discuss compression in order to deal with big size of overparameterized? Yeah, that's right. So here, so around here, so the compression is just for theoretical purpose, but it can be applied for the more practical usage. Okay, so we have very big network, but it cannot be fit to the small memory size. So therefore, we want to compress the network. So then this kind of a technique is useful. So actually, we have developed some compression-based bound based on this kind of theories. And so, yeah, so because the network can be compressed, so therefore, we can change the model size depending on the capacity of the edge devices that you want to deploy the model to. So yeah, you're right. Okay, thank you very much. Okay, so then let's go to the optimization analysis. Okay, so here I will talk some theories of optimization of neural networks. So instead of talking about some like a practical, very practical optimization technologies, but we talk somewhat a kind of principle of optimizations of neural network. So therefore, I will not talk about what kind of optimization tool is, what kind of optimizer is state of the art, something like that. But I will talk more like a theoretical thing of the optimization of neural network. Okay, so but anyway, so it is well known that the objective function, the loss function of the deep neural network is highly non-convex. So therefore, maybe the gradient descent or stochastic gradient descent can be easily stacked in the local optimal solution. But in practice, we usually see that such a solution, such a gradient descent or stochastic gradient descent can find a good optimal solution. Okay, so why is it? So it is one of the big issue of deep learning theory. Okay, so if you consider a linear deep neural network, that means that the activation function is linear. So there is no linearity in the network. So then the every local optimal solution is a global optimal solution. So yeah, as long as you're using just a linear deep network. So the linear deep network is like just a multiplication of many matrices. So for input X, we multiply, we operate one matrix, and we again, after that, we again operate another matrix. So the linear deep neural network is just some multiplication of many neurons. Many matrices. Okay, so anyway, so if you consider linear deep neural network, so then there is no local optimal solution. So this is good, but so this cannot be applied to nonlinear deep neural networks. So if there is a nonlinearity, so we cannot apply this theory. But the situation is a little bit better. Okay, so that means that if the neural network is relatively wide, so then there is no isolated local minimum. Okay, so this is a more precise statement. Suppose that we are given n training data sets, and the loss function is a convex function. So then we consider a two-layer neural network with width m, and the activation function is continuous. So then if the width m is small, width m is larger than the sample size n, so then there is no spurious local minimum. That means that every local minimum should be connected to the global optimal solution. So this is an counter examples. So this does not happen in practice. Okay, so this theorem states that this kind of phenomenon doesn't happen. So let us consider level set. So we consider this kind of threshold, and let us consider a set of x. So that gives smaller loss function, smaller loss than this threshold. So that can be depicted like this. So this is a level set below this threshold. And this theorem states that every local minimum cannot be isolated from the global optimal solution. So okay, so this local optimal solution is included in some level set that is connected, but so this region and this region cannot be isolated. So in this figure, so this region and this region is disconnected, but so the region which contains the global optimal should be connected to the local optimal solution. So the reality is something like that. So the reality is something like that. So if you are at here, so there is some path from this solution to the global optimal solution, such that on that along with that path, the loss function will not increase. Okay, without increasing the loss function, you can reach some point to the global optimal solution. Okay, and so yeah, so therefore there is no spurious local optimal solution. But here, so we should note that this theorem does not indicate that the gradient descent can reach the global optimal solution. So because there could be very large plateau, maybe the gradient descent can be captured at such a plateau. So then it is not obvious that the gradient descent can find the global optimal solution from this theorem. But actually, we can show that for a very wide network, we can find the global optimal solution. Okay, and so the intuition is like that. So if the network is very large, so then during the gradient descent, that you can find a good descent direction that increases the objective function. that decreases the objective function, that decreases the loss function. Okay. So then eventually it will find the global optimal solution that achieves the zero training error. Okay. So to analyze this kind of intuition, there are roughly two types of analysis. One is a neural tangent kernel analysis, and the second one is a mean field analysis. Okay, so I will talk about these two techniques one by one. Okay, so to explain the difference of the neural tangent kernel and the mean field regime, so let us consider the two-layer neural network. You can consider the deep network, but just for simplicity, let us consider two-layer neural network. Okay, so to initialize the network, we randomly set AJ and WJ, the second layer's parameters, the first layer's parameters. Okay, so we randomly initialize AJ and WJ. So the difference is the scaling of the such initialization. Okay, in the neural tangent kernel regimes, we set AJ as a 1 over square root m, where m is the width. In the mean field regime, we set AJ as an order of 1 over m. So there is a square root m difference. Okay. If the network size is very small, so this difference will be not so significant. But if the width is very, very large, so like in the overparametered settings, so this difference is significant. Okay. So for example, in a mean field regime, because AJ is 1 over m, so then the output is something like the average of the outputs from each neuron. So we take the average of the output from each neuron. So that corresponds to the mean field regime. But in the neural tangent kernel regimes, we multiply square root m to such an average output. So therefore, the neural tangent kernel in the neural tangent kernel regime, so there's some impact to the output. The impact of each neuron to the output is square root m times larger. Okay, so this difference of scaling is very important. Because of this difference of the scaling, so there appears a difference of the optimization behavior, and there appears a difference of techniques that we will use to analyze the behavior of optimizations. Okay. So now I'm going to the easier part, the neural tangent kernel. Okay. As I said, the parameterization of AJ is large. So this is like 1 over square root m. So then the impact of small deviation of first layer's parameter is very large to the output. Okay, so impact of the small deviation of the first layer's parameter is very large. And if you change the first layer's parameter a little bit, so the output will change very much because the scaling is very large. Okay, so because of that, we can approximate the output of the network by this Taylor expansions. You can approximate a neural network by this first order Taylor expansions. Here, W0 is an initialization. So W0 is a random initializations. So at W0, so we calculate, we consider these first order expansions. So then this can well approximate the neural network. So you can see that this is just a linear model. This is just a linear model because this is linear with respect to the parameter W. So yeah, this can be seen as one of the kernel method or kernel model. And so you can see this is a kind of a feature map. For input X, we extract a feature map by using this gradient. And then for that feature, we take the linear combination by using W. Then we get an output of the neural network. But anyway, by using this linear approximation, so any theoretical analysis of a neural network can be reduced to the analysis of this linear model. Then the problem becomes very, very easy. Okay, by using this feature map, we can define the kernel function like this. For input X and another input X prime, so we take the inner product between the feature maps. So then this is a positive, definite, and symmetric function. So we can call this is a kernel function. So this is called neural tangent kernel. You can see this is a neural tangent kernel. Okay, more precisely, neural tangent kernel is defined in a limit of m to infinity. But if m is sufficiently large, so this is almost a neural tangent kernel of the original definition. So you can say this is a neural tangent kernel. Okay, so therefore, so we can import the theories of kernel method to the neural network. Okay, so there are many theories in the kernel method, so we can import all of them to the neural network. Okay, because now, so we consider the gradient descent. Okay. So by using this representation, we analyze the behavior of the gradient descent of the neural network in the neural tangent kernel regime. So as I said, so everything is a linear model, so it is very easy to analyze. Okay, so let L hat F be the empirical risk like this, that is given by like this. This empirical, the training loss is denoted by L hat F. And we optimize this empirical risk by using a gradient descent. So just for simplicity, we consider continuous time dynamics. Okay, dt dwt is given by minus the gradient of the objective function, gradient of the loss function. Okay, so we consider this dynamics. So then the dynamics of the function value can be evaluated like this. The time differentiation of the function the value fwt is first given by like this. So this is just chain rule. Okay, so because of the chain rule, we first take the time differentiation of wt, and after that we take the gradient of the function value like this. Okay. And because we are considering the gradient descent, so dt dwt is given by minus of the gradient of the loss function. So then this can be replaced by this one. Okay, so because the loss function can be decomposed into like this, so it can be decomposed. So this gradient can be decomposed into like this. And for each loss functions, its derivative is given by like this. So here we again apply the chain rule. So, but we apply the chain rule. So first we calculate the gradient of the function value, and the next there appears the derivative of the loss function. Okay, now we move this derivative to the outside the inner product. Then you can find that there appears an inner product between this one and this one. So yeah, so this one. So there appears an inner product like this. So here, remember that the function value fwx can be approximated by this linear model in a neural tangent kernel regime. So therefore, this inner product is obtained by the neural tangent kernel. And also the neural tangent kernel is defined at initialization. So this is invariant during the optimization. Okay. So so this term does not change during this term does not change during the optimization. So then it makes much easier to analyze the dynamics of the optimization. Is it clear? Okay. Okay, so now we use this evaluation to evaluate the value of the loss function, dynamics of the value of the loss function. So here we take the time differentiation with the loss function, the empirical loss function. So by using the chain rule, we have this expansion, the time differentiation of the function value times the derivative of loss function. Okay, now we substitute the previous slide's result to this term, then we get this expression. Okay, we get this expression. So you can see that there appears a quadratic form. And remember that this is a kernel function. This is a positive definite. So this can be written by like this Kij. So K is a kind of a Gram matrix. K is a Gram matrix. So its ijth element is this one. So yeah, so we can see that this is a kind of a norm which is defined by this Gram matrix. Okay. And now we assume that the minimum eigenvalue of the Gram matrix is greater than 0. Okay, so lambda minimum. So we denote by lambda minimum the minimum eigenvalue of the Gram matrix, which is not less than 0. So which is non-negative. So then this quantity can be upper bounded by this quantity. Okay, so we can remove k from here. So then lambda minimum appears here. Okay. So anyway, so this is just a summation of a square of the gradient of the loss function. And so this is a positive value. And so this is also the positive value. And then, so therefore, until the gradient of the objective function converges to 0, so then the objective function will continue to decrease. So okay, so here's one example. Okay, let us consider a regression problem where we employed a squared loss. We employed a squared loss. So then by substituting this loss function to this evaluation, so then the time differentiation of the loss function, the empirical loss can be bounded by minus the positive value times the loss function itself. Because the derivative of the squared loss is just a yi minus fxi. So by taking its square, like this, by taking its square, we again obtain this quantity. So this is just nothing but this is nothing but empirical risk. Okay. So therefore, by applying so-called Gromov inequality, so we obtain the linear convergence of the objective function. Okay. So unless this value converges to 0, the time differentiation of the loss the objective function that does not converge to 0. Therefore, we obtain exponential convergence like this. Okay, so this is an illustration of the neural tangent kernel regime. Okay, so here's a more explicit and precise statement of the dynamics of the neural tangent kernel regimes. Okay. Let us consider a regression problem. And if the width m is sufficiently large, so then the grand descent can converge to a solution with 0 training error, which has a generalization gap like this. And also this convergence is a linear rate. Okay, so this is because if the width is like order n squared divided by some quantity, the minimum eigenvalues. So then so we can consider this approximation. So for very wide networks, so this approximation is valid. So then we can apply this this argument. So then we can show that the grand descent can converge to a solution in an exponential order. Okay, and also under some assumptions, under some conditions, we can show that the minimum eigenvalue or the minimum eigenvalue of the Gram matrix of the neural tangent kernel can be lower bounded by 0. So this is actually positive. So therefore, so that this width m is finite. So even though the width can be very large, but this is finite. So okay, so for the large network, so we can convert to 0. And moreover, there is a generalization gap that is given by like this. Here, k infinity is almost the same as k itself. So you can consider the k infinity as a Gram matrix. But anyway, so we have some generalization gap found. So this is good. So we can find a global optimal by a gradient descent, and also there is a generalization gap found. But the one problem is that there appears the minimum eigenvalues, and also there appears the inverse of the Gram matrix. So therefore, the inverse of the minimum eigenvalue has a large impact to this result. So in other words, if the minimum eigenvalue is very small, so then this generalization gap could be very large. Okay, so actually, if the output y has some noise, like if the output is like a noisy observation, so there is no guarantee that this generalization gap converts to 0 as the sample size n goes to infinity, because there is an inverse of the Gram matrix. Okay, so that's a bad point. But but we can show that in the letters from now. So in the following, we can show that this small eigenvalue is a kind of beneficial to show a good generalization performance. Okay. Okay, so this figure shows the behavior of the eigenvalue of the Gram matrix. Okay, so the eigenvalue of the Gram matrix is sorted like this. If the sample size is n, the sample size n is around here, so then the minimum eigenvalue of the Gram matrix is around here. So this is a pretty small. It is like a 10 to minus 9 or something like that. So this is very small. The lambda minimum is like a 10 to minus 9. So that comes here. So lambda minimum comes here. So that is very bad. but we can show that this kind of small eigenvalue is a kind of beneficial for the generalization. Okay, so I will explain that from now on. To understand that, the kernel smoothing viewpoint is very important. So, okay, the grand descent in a kernel method can be seen as like a smoothing operation. During the optimization, we can show that the grand descent performs something like a low pass filters, and so high frequency component is suppressed during the optimization. Okay, to understand that, so remember that the time differentiation of the function value of our model can be obtained by like this. You can see that at each time t, so the update is obtained by applying the kernel function to the derivative of the loss function. Yeah, then we can see that the derivative of the loss function is a kind of residual. Okay? So if this derivative is 0, so there is no residual. But if this derivative is large, so there is a huge gap between the output from our model and the levels, so supervised levels. So there is a gap between our output and the supervised signal. So therefore, we can see that this is a kind of a residual. So yeah, so that means that at every iteration, so we are operating the kernel function to the residual. So here we can see that the kernel matrix, this kernel function is a kind of smoothing operator. So usually the neural tangential kernel is smooth. So then by operating this to the residual, so we can realize a kind of smoothing operator. Okay, so here is more precise and detailed analysis. Okay, so just for simplicity, let us consider squared loss. So then the derivative of the loss function becomes like this. So this is just a residual. This is the gap between the level y, the training level yi, and the output from our model. So this is a residual. And now we apply the so-called Mansell decomposition to the kernel function k. Okay, so we require some function analysis theorems, but anyway, so and the kernel function k can be decomposed into like this. So here mu l is so-called eigenvalue, and the phi l is the eigenfunction, and the phi l are mutually orthogonal in the L2 space. Okay, phi l is like a basis function also known as basis function in the L2 space. So yeah, they are orthogonal in the L2 space. Yeah. So that okay, so that the kernel function can be decomposed into like this. So mu l is an eigenvalues, and we can theoretically show that the eigenvalue drops in a polynomial order, and also the phi l for small l. That means the phi l for a large eigenvalue corresponds to the low frequency component. Okay, and if the index l goes up, so then the eigenvalue of the mu l will drops, and for small eigenvalue component, that means for large index L, the phi L corresponds to the high frequency component. Okay, so therefore, for the low frequency component, the eigenvalue mu L is large. For a high frequency component, the eigenvalue mu L is small. So now we apply this to this formulation, so that we have this formulation. Okay, for each residuals, for the residuals, we extract the component of phi L. Okay, so this is like an inner product. So we extract a coefficient or component. We extract component corresponding to the phi L from the residual, and then for that coefficient, we multiply the spectrum. We multiply the eigenvalues. Okay, so if L is large, we are extracting low frequency component from the residual, and then we multiply large eigenvalue. But if L is large, so then we extract the high frequency component from the residual, and we multiply the small eigenvalue. So this means that we extract, we decompose the residual to the components that correspond to each eigenfunction, and then for each component we multiply the eigenvalues. So then, so by doing so, we can suppress the high frequency component. we only extract the informative, so low frequency component from the regional. Okay, so then so that means that we extract just a low frequency or principal component from the regional, and then it is incrementally added to the function value. Okay, so therefore, at each iteration of the gradient descent, we are using something like a smoothing filter by a kernel function, and then the high frequency component is suppressed, and just only low frequency component is extracted, and it is added to the function values. Okay, so this is the kernel smoothing viewpoint of the gradient descent. Yeah. So because of that, so we can suppress overfittings, because overfitting appears for overfitting appears by a fit of a high frequency component. So by suppressing such a high frequency component, we can avoid the overfitting. Okay, so then we want to analyze the behavior of the gradient descent in a precise way. So then let us consider the two-layer neural network in a mean field regime, in a neural tangent kernel regime. Okay, the scaling is 1 was greater than n. So let us consider to optimize the empirical, expected loss like this. So we want to minimize the mean squared error. But just to minimize this one, we lead to overfitting. So we add some regularization. So this is basically L2 regularization, but this is a little bit different from the practical use. So we consider L2 distance from the initialization. So this is just for the theoretical purpose. But anyway, so we consider this regularization. And then we consider online stochastic gradient descent. At each iteration, we sample 1 data point. Okay, so at each iteration, we sample 1 data point. By using this data point, we update the parameters by using the gradient descent. Now we iterate this. So this is an online stochastic gradient descent. So then so how it will converge. So this is the result. And we can say that the SGD can achieve the so-called minimax optimal rate. Okay, so here FT denotes the solution after the T iterations. Because after the T iterations, the L2 distance from the true function can be bounded by this quantity. So here the first term is a quantity that can decrease to 0 as the width m goes to infinity. So yeah, this term can converge to 0 for very over-parameterized settings. And the main term is the second term. So here, remember that we are considering the online optimization settings. So the T corresponds to the number of observations that we have observed. So that means the T is the same as the number of training data points, the sample size n. So you can replace T by a sample size n. And you can see that this learning rate is faster than 1 over squared n. The 1 over squared n is a typical learning rate that can be derived by Rademacher complexity. For example, you can see 1 over squared n convergence rate like this. So this is given by Rademacher complexity analysis. But we see faster learning rate than 1 over squared n. So then this is called fast learning rate. This is called fast learning rate. Okay, so the learning rate, the convergence rate of this fast learning rate is characterized by 2 quantities, R and beta. So what is R and beta? So first, I want to explain beta. Beta controls the decay rate of the eigenvalues. Okay, so remember that the neural tangent kernel can be decomposed into the eigenvalue and the eigenfunctions. So, and we assume that the eigenvalue drops in a polynomial order, like mu j is order of j2 minus beta. So if the eigenvalue drops faster, so then beta becomes large. So therefore, the decay speed of the eigenvalue affects the convergence rate. Yeah. So therefore, if beta is large, so we have very small eigenvalue, so minimum eigenvalue of the ground matrix. So roughly speaking, the minimum eigenvalue of the ground matrix corresponds to mu n. So n is the largest eigenvalue of the neural tangent kernel. So yeah, so mu n. So therefore, the minimum, so lambda minimum that appeared in the previous slide. So here we see that lambda minimum is the minimum eigenvalue of the ground matrix. The ground matrix is n times n large. So therefore, roughly speaking, the lambda minimum is mu j, where j is n. So roughly speaking, in this case, the lambda minimum is like n2 minus beta. Yeah. So therefore, beta controls the decay of the eigenvalues. And you see that if beta is large, the running rate becomes faster. Okay. So this contradicts the previous result. If lambda minimum is small, so that we have a larger generation gap. But in this case, we can see that if beta is large, so that means lambda minimum becomes small, we have a faster running rate. So why is it? So because here we are assuming some little bit strong conditions where the true function f star is nearly included in our model. Okay, so we are considering the neural tangential kernel regime. So then the neural network FW can be approximated by the linear model. And we assume that the true function is included in that model. Okay, so that is a kind of a strong assumptions. But under such assumptions, the rapid eigenvalue decay is beneficial. Yeah. So there's also another quantity R. So R, what R represents? So R represents the relative location of the true function. If the true function is included in very small subspace of our model, so then R can be large. But if the true function is nearly outside of our model, so then R can be small. Okay. So then, so in that case, if the true function is almost outside of our model, so then R can be small. So then the rate of convergence becomes slow. So you see that there appears some variance and variance trade-off. Okay? If beta is large, so then the eigenvalue drops rapidly. So that means the model becomes simpler. It has a less expressive ability. So in that case, maybe R could be small. Because for a simple model, so maybe the true function can be easily outside of the model. But if beta is small, that means that the model is more complicated. So then the true function can be easily inside the model. So then we have a large R. So there is some trade-off between R and beta. Okay, so here the interesting point is that such a trade-off is completely determined by the shape of the network. So in other words, this bias and variance trade-off is characterized by just random initializations. So yeah. So therefore, so we can say that is kind of an inductive bias. Okay. The network itself has some network itself has some inductive bias, and based on that inductive bias, so we have a different convergence rate. Okay, so through this kind of smoothing filter viewpoint of the grand descent, and the early stage of the grand descent, it captures the low frequency component. So after that, it gradually captures high frequency component. So then if you stop here, then you can avoid overfitting. Then eventually you get this fast running rate. And another way is that you impose appropriate regularization. So then you can avoid the overfitting. Then you get this fast running rate. Yeah. So this kind of behavior oftenly observe the developing optimization of a neural network. The neural network first captures the low frequency component. After that, it gradually captures high frequency component. Okay, so here is a more precise description of the inductive bias of a neural tangent kernel. We can theoretically show that the eigenvalue drops in the polynomial order, and also eigenfunction corresponds to a kind of frequency. For example, if the input x is a uniform distribution on the sphere, and also the initialization is given by like this, A and W randomly initialized by normal distribution. So then the neural tangent kernel can be decomposed into like this. But first, the eigenvalue drops in order of the K2 minus T. So yeah, we have a polynomial order decrease. And moreover, so YKJ is appearing here. So this corresponds to the eigenfunctions. So this corresponds to the special. So the eigenfunction is given by spherical harmonic function with degree k. So therefore, as k increases, that is the index increases. So then the corresponding eigenfunction has a high frequency component. So as the index k increases, so then the eigenfunction becomes more high frequency. Okay. So this theorem justifies my explanation in the previous slide. Okay. So I skip this one. Yep. So by using the neural tangent kernel regime, so we can analyze the behavioral optimization of neural networks by using the kernel method. So, so in the first part, so in yesterday's talk, so I said that the neural network can outperform the kernel method. And so therefore, if the neural network can be approximated by the neural tangent kernel, so then everything is included in the framework of a kernel method. So we cannot show the neural network can outperform the neural tangent kernel. So neural network can outperform the kernel method. Okay, so therefore, to analyze the superiority of neural networks, so we needed to go beyond the neural tangent kernel regime. Okay, so as long as we are in a neural tangent kernel regime, so we cannot show the difference between the neural network and the kernel method. So therefore, so we need to go beyond the neural tangent kernel. So then that analysis becomes much difficult. So there are many papers that attempt to go beyond the neural tangent kernel. For example, if you're interested in, please look at these papers. Okay. But I consider a kind of a different direction. Okay, so that is a noisy gradient descent. So this is also one of the hottest topics in the current theoretical researches of the optimization. Okay, so as I said, the neural network is highly non-convex. So therefore, the optimization landscape maybe looks like this. But the gradient descent, or stochastic gradient descent in practice can find a good solutions that can generalize well. So why is it? The stochastic gradient descent is not captured by very bad local minimum, but it can find a nice solution. Maybe it will be a global optimal solution. So why is it? So there are many explanations about the success of the stochastic gradient descent. But one intuitive explanation is that the SGD is a noisy gradient descent. So therefore, because of that noise, so you can escape from the local optimal. Okay, so at each iteration, there is a noise. So therefore, the solution is perturbed. Then you can get out of the local optimal. Then you can find the global optimal. So this is one intuitive explanation about why SGD works well in practice. There are also another support of the SGD. Okay, so that is the so-called sharp minima and flat minima argument. Okay, so in this figure, the black line explains the training error, and the red line expresses the test error. Okay, so because training data behaves randomly, so the training error is a little bit different from the test error. Okay, so now we consider to use the stochastic gradient descent. Maybe stochastic gradient descent, so the solution can be captured here. So this is a sharp minima. This is called sharp minima because the landscape around here is very sharp. So this is called the sharp minima. So then in this case, the difference between the training error and the test error is very large. So this is just an intuitive explanation. So this is not a rigorous argument, but you can see that this is there appears a very big difference between test error and training error. So therefore, if the solution is captured in a sharp minimum, it's not good for the generalization error. Okay, so therefore, it is better to achieve the flat minimum. But as I said, SGD is a noisy gradient descent, so it perturbs like this. It is randomly perturbed. So therefore, it can easily get out of the sharp local minimum, and then it can find the flat local minimum. So if the landscape is very flat, so it is not so easy to get out of this flat minima, even though we have some perturbation. So this landscape is very, very flat. So it is very much easy. It is not easy to get out of this this region to another regions. So we need very large fluctuations. So therefore, the SGD is likely to be captured by flat minimum. And if you are at the flat minimum, so it is good in terms of the generation error. So because you can see that the discrepancy between test error and the training error is very small around here. Okay, so therefore, SGD is good for the generalization. Okay, this is one support for the usage of SGD. So another explanation is that SGD can smooth out the loss functions. Let us consider this kind of very deviated loss functions. And so, as I said, SGD is a noisy gradient descent. So because of that noise, so the SGD convolutes out the loss function by using a this noise. So I mean that we take the expectation with respect to the noise. So then we can do something like a convolution of the noise, the convolution between the noise and the objective function. So then we can smooth out the objective function like this. So then SGD behaves as if it is optimizing this smoothed objective function. So because of that, it can find the global optimal solution. Okay, so it does not capture in this kind of flat, this kind of sharp local minimum. Because of the noisy fluctuation, it can easily get out of this sharp local minima, and it can eventually find the global optimal solution. So this is another viewpoint. So we want to characterize this kind of analysis in more general settings. Okay, to do so, we consider gradient arrangement dynamics. That can be written by this stochastic differential equation. Okay, so maybe so we should consider stochastic gradient descent itself, but here we consider a kind of idealized settings. For the theoretical purpose, we only consider really idealized settings, where the noise of the gradient is given by Gaussian noise. Okay, so I briefly explain this stochastic differential equation. So dxt is given by minus the nabla of the objective function. So if you stop here, so this is just a gradient descent. This is just a continuous time gradient descent. But there is a Brownian motion term. So this corresponds to the noisy perturbation of the gradient descent. But this is a continuous time dynamics. So let us consider discrete time settings. So this is much more easier to understand. Okay, so xt plus 1 is given by xt minus step size eta times the gradient of the loss function plus Gaussian noise. Okay, so this Gaussian noise works as a noisy perturbation. And you can see that there is a parameter beta. So beta is a so-called inverse temperature parameter. Okay, so beta controls the strength of the noisy perturbations. If beta is large, so then the noise can be small. So yeah, so beta controls the strength of the noise. So this is called gradient arrangement dynamics. If you replace this gradient by a stochastic gradient, so then this is called the stochastic gradient arrangement dynamics. Okay. Oh, maybe so I should mention it before we start. So okay, so I said it yesterday, but today I'm also sharing the slide in the I'm sharing the slide in the link I have sent via chat. So if you want to see the slide, so please look at that slide, that link. Okay, so now anyway, so I continue my talk. Okay, so because of this noisy perturbation, so you can escape from the local minimum, and it can eventually find a global optimal solution. Okay, so this can be rigorously shown. Okay, so I want to explain that a little bit more. Okay, so one important property of the gradient arrangement dynamics is that the continuous dynamics, so this continuous dynamics has a stationary distribution. That means that the distribution xt converges to this distribution as t goes to infinity. when you run the gradient enlargement dynamics a very long time, so then the distribution will become like pi infinity given by this quantity. Okay. So the stationary distribution is given by exponentially minus beta times the objective function. So the Fx is what we want to minimize. So basically, this is a empirical risk. So yeah, the objective function is coming here. So therefore, the stationary distribution concentrates around the global optimal solution of Lx. So this is the illustration of the density function of the stationary distribution. So that can be given like this. The maximum value of the probability density function of pi infinity is achieved by the minimum. So the optimal of the Fx. Okay. So the maximum value of the distribution, so density function pi infinity is achieved by the optimal solution of Lx. So that minimizes the objective function. So because here is minus, so yeah, the minimum and the maximum is flipped. And you can see that as beta is increased, so then this shape becomes much more sharp. Actually, if beta is like infinity, so then pi infinity is something like a Dirac measure put it on the optimal solution on the objective function. Okay. So therefore, for large beta and large t, so the solution xt will concentrate on the global optimal solution. So actually, so instead of staying around here, so the solution will likely to stay around the global optimal solution. Okay. So therefore, even if there is some small, even if there is some sharp local minimum, because from this observations, so it is likely to be outside of such a sharp local minimum, and so it will reach flat global optimal solution. Because if it is flat, so the probability there is, the probability mass around there is large, so then the solution is likely to stay around there. But if this shape is very sharp, so then probability mass around there is very small. So that means that xt does not stay around there. Okay, yeah. So the next question is, so even though this is a stationary distribution, so how fast xt converges to this distribution? So that is the next question. And to characterize the convergence rate, the important quantity notion is the so-called log Sobolev inequality. Okay, so this is a little bit difficult notions, but this is very convenient to analyze the log Sobolev inequality. Okay, suppose that there is another distribution nu that has a density function, and the ratio of the density pi infinity and nu is given by some function f. We consider this kind of settings. So then if every f satisfies these conditions, so then it is called, then we can say the pi infinity satisfies the log Sobolev inequality. Okay, so in the left-hand side, there appears the KL divergence between nu and pi infinity, because f is a density ratio between pi infinity and nu. So this is a KL divergence. In the right-hand side, there is a so-called Fisher divergence. This is so-called Fisher divergence is coming here. The Fisher divergence gives an upper bound of the KL divergence. Then we call pi infinity satisfied log Sobolev inequality. And the intuition is a little bit difficult to give some intuition. Well, one viewpoint is that we want to minimize the KL divergence between nu and pi infinity. So we want to converge xt to pi infinity. Okay, to analyze that, we take some derivative. Okay, so we type, because we are considering something like a gradient descent, we take a derivative. So that corresponds to the Fisher divergence. You see there is a gradient of f. So here is what we want to minimize. And so what we want to minimize is bounded by a kind of a gradient of the objective function. Okay, so therefore, because of that, by making the gradient to be 0, for example, by using the gradient descent, the gradient will going to 0 after many iterations. So then we can ensure that what we want to minimize can also be minimized. Yeah, something like that. Okay. So this is a little bit kind of related to so-called PL condition in optimization. Okay, so under this logosovereign inequalities, we can show the geometric ergodicity. That means that the rho t is the marginal distribution of xt. The xt distribution, the distance between the xt distribution and the extension distribution converges to 0 in exponential order. The rate of the convergence is characterized by the log Sobolev constant appearing here. This is called the log Sobolev constant. Yeah. Okay, so from these observations, maybe so it is very important to analyze the log Sobolev. Oh, sorry, there appears some typo. Okay, so something is lost here. Okay, so okay, I explained by using my voice. Okay, so here's some examples in which the log Sobolev constant is bounded. Okay, so first we consider a situation something like that. So the Lx, the objective function, is obtained by the loss function, empirical loss, plus the L2 regularization. And here we assume that L1, Li, the loss function, is bounded. Okay, so this is a bounded function plus the squared, the quadratic function. For in that case, the log Sobolev constant can be bounded. So it is like 1 over lambda 1 beta times exponential 4b lambda 1. So exponential 4b beta will come in here. But anyway, by using this bound, upper bound, and so lambda 1, we can characterize the log Sobolev constant. The log Sobolev inequality can satisfy for these situations. And another important example is the convex case. If the loss function is mu strongly convex, or objective function is mu strongly convex, so then the log Sobolev inequality satisfies where CLS is bounded by 1 over mu beta. Okay. Another important example is this kind of dissipative condition. If the objective function satisfies this condition, so it is called dissipative objective function. So intuition behind this, or maybe so I have missed again. So okay, so this is not the less than equal. So okay, this inequality should be flipped. This is lower bounded by m to x squared minus b. So okay, so I will modify. So I will modify. I will fix this one, and I will re-update this slide again. But anyway, so this inequality should be flipped. So okay, so x times natural Lx is lower bounded by m to x squared minus b. So this is the precise definition of the dissipative condition. Well, so intuitively, so this dissipative condition means that the objective function is supported by quadratic function from below. Okay, so maybe it is not convex functions, but outside of some regions, it is like a quadratic function. Okay, so that the objective function is lower bounded by the quadratic function. So this is a dissipative condition. So if the objective function shapes like this, so then the solution cannot be very far away from the origin. So because it is supported by the quadratic function below, so by applying the grand descent, so it can return the solution should return to this region. So then by applying some low-G perturbation, eventually it can find a global optimal solution. And we also assume the smoothness of the gradient like this. The gradient is Lipschitz continuous. So then the log Sobolev inequality is satisfied like this. So you can see that this is one example of dissipative conditions. Okay, because this is a quadratic function and this is bounded. So yeah, so this function can shape like this. Okay. Yeah. So under such a log Sobolev inequality assumptions, so we can show that the discrete time solutions, so that discrete time dynamics also converge to near stochastic distribution. Okay. Now we assume that the objective function is m smooth, so it is smooth. So then it converges in exponential order. Okay, sorry. So instead of d, so m should come here. So m squared should come here. Okay, so anyway, so the first term converges in exponential order with respect to the step number of steps k. And if the second term can be very small for a small step size eta. Okay, so therefore, the marginal distribution of the discrete time dynamics xk will also converge to the near the pi infinity, near the stationary distribution of the continuous distribution, continuous time dynamics. And also in terms of the optimization, we can also show this kind of a bound. So this is coming from basically the Pan-Shu's paper in 2018. Okay, so the objective function of time k minus the optimal solution, optimal value is bounded by the first exponential order term plus order eta term plus 1 over beta term. The first term is coming from the geometric ergodicity I have shown in this slide, and the second term is coming from the time discretization error. Okay, so if the step size eta is sufficiently small, so this term is also negligible. And the third term is coming from the discrepancy between the stationary distribution pi infinity and optimal solution. So this term shows how strongly concentrates the pi infinity around the global optimal solution. Yeah, so that is controlled by the inverse temperature beta. So therefore, if you set inverse temperature beta sufficiently large, so then this term can be very small. And accordingly, so if you set the time discretization error sufficiently small, that means that if you use a very small step size, then this term can be very small. And finally, if you iterate the iteration many times, so that means k goes to infinity, then the first term goes to 0 in exponential order. Yeah, but I should say that there is no free lunch. So because the log Sobolev constant depends on the inverse temperature beta in the exponential order in many cases. For example, in the dissipativity conditions, there is an exponential beta terms. So the log Sobolev constant can be exponential to the beta. So that in the worst case sense, so the Granic-Langevin dynamics should pay exponential number of iteration, or exponential number of exponential large computational cost. But as I said, so if the objective function is mu strongly convex, there doesn't appear exponential orders. So therefore, if the objective function looks like this, so then xt converges around here. So then locally, it looks like a convex function. Locally, it looks like a convex function. So then, after sufficient number of iterations, it is captured in the local convex regions. Around there, the CLS, the log Sobolev constant, is altered by this one. So then you can avoid the exponential dependency on the beta. So therefore, I think that in reality, so we have a much more efficient convergence. Yeah, but in theoretical sense, the worst case error has an exponential dependency on the inverse temperature beta. Okay, so I want to stop this this kind of thing. Okay, so here is some another remark on the Granic-Langevin dynamics. Okay, so you can consider the infinite dimensional version of the Granic-Langevin dynamics. Then we can show the convergence, even though the dimensionality d is infinity. Okay, so let's come back to this bound. You can see that, for example, in this case, if for the dissipative conditions, so the dimensionality d appears here. So for very high dimensional case, the log Sobolev constant becomes very large. So we cannot guarantee a convergence. For example, for the infinite dimensional case, we don't have any good guarantee for the convergence. But under some assumptions, we can show the convergence even though it is an infinite dimensional case. Okay, so here's here's a brief explanation. Okay, so here FW is like a model with parameter W. So here W has an infinite dimension. W can be infinite dimensional. For example, 2-layer neural network or ResNet, something like that. And we can allow the 2-layer neural network be the infinite width. Okay, so we basically want to optimize this model, and by minimizing this loss function. But so by just optimizing the loss function leads to that some overfitting. So we add regularization. Okay, the point is this regularization. So for this regularization, instead of just a usual L2 regularization, we consider this kind of weighted sum of the square of each component of W. So this is a kind of RKH zone. So if you are familiar to the Kernel method, this is something like the RKH zone. Okay, so we consider the weighted sum of the each component, weighted sum of the square of each component of the parameter W. So if we consider this kind of a squared L2 regularization, so we can show convergence of the statistical, we can show the convergence of the gravitational Riemann dynamics in the infinite dimensional space to the stationary distribution. So accordingly, we can also show the convergence to the global optimal solution of the objective function. Okay. So finally, I want to mention a little bit about the mean field analysis. Then I want to finish my tutorial. Yeah. So far, do you have any questions? So if you don't have, so I want to finish it quickly. Okay. So okay, so let us consider the mean field regime. So the mean field regime was given like this. So as I said, the scaling is different. Instead of 1 over square root m, so we consider 1 over m. Okay, so this is a 1 over m. So this is a kind of average of the outputs from each neuron. So this is an average. So this is different from the neural tangential kernel regime. But unfortunately, this is nonlinear with respect to the parameters Rj and Wj. So this is nonlinear. So that makes difficult to optimize this network. Okay, so therefore we consider a kind of m to infinity limit. We consider asymptotic of m to infinity. So then this finite sum will converge to this integral representation. Yeah. So here nu is the distribution with the parameters R and W, the second and the first series parameter. Okay. So then by using this integral representations, we can see that this is linear with respect to the distribution nu. Okay, so if nu has some density function, so this is linear to the density function Q. So therefore, it becomes much easier to analyze. Yeah, that is one ingredient of the mean field regime. So this is an important viewpoint. Okay, now we assume that each particle. So let us consider the particular approximation of this integral representation. So I mean, we sample IID particles from this distribution of the parameters. Then by using the particles, we can define this finite sum. So therefore, we can see that the usual finite sum network is a particular approximation of this integral representation. Okay, so that means that each neuron corresponds to each particle generated from this distribution. Okay, we assume that we consider that each particle moves to direction Vt, so that it minimizes the loss function. So this is just a gradient descent direction. Vt is a gradient descent direction of each particle. Okay, then all particles all particles move along with this vector field, so that it can minimize the objective function. So then accordingly, there appears a dynamics of the distribution nu. And then the distribution of the dynamics of distribution is written by this quantity. So if each particle move along with the vector field Vt. So this is called continuity equation. Okay. So this is a little bit difficult. So mathematically very difficult, but anyways, we can describe the dynamics of the distribution nu. So then by analyzing these continuity equations, so we can show that it can converge to the global optimal solution. Okay, so this is a little bit technically difficult, but you can show that. But to show the global convergence, we need some more, some strong assumptions. Therefore, we usually consider a noisy gradient descent. instead of just a gradient descent, each particle has a so noisy perturbations like this. Okay, so instead of just optimizing by using the gradient descent, we consider a kind of noisy gradient descent. So then the dynamics becomes so-called Markine-Vlasov process. Okay, so each particle moves with interactions. There are many interactions. So each particles are interacting, and then it optimizes the objective function. That is called the Markine-Vlasov process. And then corresponding dynamics of the distribution of the particle is given by this one. So this is a different point from the non-noisy gradient descent. Yeah. Anyway, so we have this explicit form of the equations. By analyzing this, we can show the global optimality of the dynamics. So, for example, please look at this paper. So then you can see some details. Okay. So, but this kind of analysis is very difficult. So yeah. So therefore, we have proposed some other method, so-called particle dual averaging method. Yeah, so if you use this method, so we can show the convergence in very compact, yeah, so like this. So we can show the global optimality in a very simple expressions. Okay, to obtain the epsilon optimal solutions, so just an epsilon to minus third gradient descent evaluation, the gradient evaluation is sufficient. So if you use our techniques, so I skipped some details of the proposal, but anyway, so if you use such a technique, so then you can show the global optimal convergence with the polynomial order computations. The main gradient, the important point is that the objective function is convex with respect to the density function Q over the parameter theta. So by using that notion, so we can apply the theories of the convex optimization to this mean field optimization. So then by doing so we can show the convergence to the global optimal solution. Okay, so then I want to summarize my tutorial. Okay, so I have presented 3 topics of the deep learning theories. One is representativity, and in this categories I have talked about the adaptivity of deep learning. Because of that, the deep learning can outperform the kernel method. The second category was the generalization ability. So in these categories, I have talked about some generalization gap analysis. The one is a norm-based bound. The second one is a compression-based bound. In this bound, we analyze the intrinsic dimensionality of the model. And the third one is optimization ability. So in these categories, I have talked about 3 topics: neural tangent kernel, and noisy gradient descent, and mean field regime analysis. And for the neural tangent kernel regime, so by looking at the spectral bias, so then the fast decay of the eigenvalue could be beneficial for the generalization. And also we can confirm the global optimality of the gradient descent. And as for the noisy gradient descent, so the log topography inequality was important. And the third one is mean field regime. So by looking at the dynamics or the distribution with the parameters, we can show the global optimality of the dynamics. Okay, so I hope that this kind of deep learning theory could be helpful to make the deep learning more white box. And I hope it will be useful to make deep learning more controllable. Well, and moreover, so I hope that this kind of deep learning theory is a kind of helpful to reveal the essence of the good learning system. And so by doing so, it will be useful to develop a new method that could be beyond the deep learning. Okay, so if we have some theoretical intuition about why the deep learning works well in practice, so then maybe it will be useful to develop a new method that can be beyond the deep learning. So, but unfortunately, the current situation of the deep learning theory is not as high as this level. So we need more theories. So, but yeah, I hope we and you will develop more theories, and on top of the current state of the theories, and so you will open up some new theories that could be useful for beyond the deep learning. Okay, so thank you very much.